Let's move on to the next topic, and this is logarithms. Let's try to define what is a logarithm. Okay. Logarithm, in order to define a logarithm, I should always have a relationship such as a to the power x is equal to b. Right? Here, there is a condition, a should be always greater than 0, and this is first condition, and a is not equal to 1. Let us consider any equation like this. Okay, like 3 to the power 2 equal to 9. Right? You can see a, b, and x are different. Right? So, okay, such an equation is considered. Right? If I'll write if a to the x equal to b, right, then x is called as the logarithm of b to the base a. Right? So we can write this as this log of b to the base a equal to x. So whenever I see like this, it is also can be written in this fashion. So you see, we bring a term called log, right? That is log of b to the base a equal to x. Right. Again, from this equation, the newly written equation, which includes log, it is very clear that b will be definitely greater than 0, right? So this implies b greater than 0 for sure, right? And if at all I try to write, okay, let me write it over here, right? So this is the only point which I have to write. So from this particular equation, it's very clear that the b is also greater than 0. So this implies b is greater than 0. So we can actually interchange wherever I see a to the power x equal to b, right? I can interchange that with log of b to the base a is equal to x, right? So this is both these equations are equivalent, right? They are one and same. Okay, so this is what is the fundamental equation that corresponds to the log, right? Normally, something raised to the power by a power can be replaced by log in this fashion. Now, depending upon what is the base, right? So we call it as a different bases. All right. So if, say, in case if a is considered as 10, right? So this means the base 10, right? Something like log of b to the base 10, right? Normally we write it in this way. At the same time, if a is equal to e actually has a specific value. E is equal to 2.7182. Then log of b to the base e is called as lnb, another short form. So where ln stands for log natural. So we call it as the natural log of b, right? So if at all the base is 2.7182, there is a very specific application with the base e, right? Which as of now we don't have to consider. It will come at a later stage. So if you have a base as e to the e, right, that is 2.7182, it's actually called as a Napier's constant. That 2.71, most of the scientific calculations do based upon that e value. So we might have to take the base e also sometimes, right? So for that reason we need this. Okay, so these are the common bases which we take. One is base 10, one is base e. Now let's try to remember, if we don't specify any base, that is always base 10. Okay, right. Let's try to remember some of the standard log values. The first one is log 2. When I say log 2, it always means that log of 2 to the base 10, 0.301. Right? You might require this to be substituted at some places. Then we have log 3. Again, this is log of 3 to the base 10. That is 0.4771. Then we require ln as well. ln2, natural log of 2 is log of 2 to the base e, right? So that is 0.693. The ln10, this is ln10 is log of 10 to the base e is 2.303. So these are some of the values which we require. Right. Then let's take up a note. Right. So there is one property. We'll look at the various identities related to this. So first one is, if I have a to the power log of b to the base a is equal to b itself. So this particular rule is called as the fundamental logarithmic identity. All right. If at all we try to write a function such as f of x is equal to log of x to the base a, right? If you see any equation like this, this is called as a logarithmic function. All right, then let us consider a situation where we have a to the power x is greater than 0. I'll write if a to the power x is greater than 0 for all values of x belonging to any real number. Right, we have two possibilities. The first possibility is if a to the, or let's say if a is greater than 1, right? So this implies if a is greater than 1, then a to the x is going to increase continuously. So we can call it as, it's a monotonic or monotonically increasing function. It increases, right? So as the x increases, you can see that it increases, right? At the same time, if a is less than 1, right, then a to the x is decreasing, monotonically decreasing, right? So that's the one property which we need to remember. Okay, anyway, a to the x can be actually, if a to the x equal to b, I'll still convert this into a log function and I will use it. So for that reason, we have to remember this. Right, then next one. Right, so if a is greater than 1, this implies if I write a to the minus infinity becomes equal to 0, right? So actually this implies log of 0 to the base a, right, is nothing but minus infinity. So this is important. So this is a specific case with a greater than 1 only. Okay, and let's look at the other case. So here, if 0 less than a less than 1, right, then a to the power infinity is 0. Okay, so here you see the log of 0 to the base a becomes plus infinity. So under which case it is between 0 and 1. So we have quite differences coming into picture. Okay, so log of 0 becomes plus infinity or minus infinity because of that reason. Right? It depends upon what is the value of a, what base you are considering. If the base is greater than 1, answer is minus infinity. If the base is between 0 and 1, the answer is infinity. All right, let's move further. Then the next important point related to this is log of b to the base a, right, tends to infinity. It is not infinity, it goes closer to infinity. It becomes a very large value, right, if a is greater than 1 and the b is going close to infinity. B becomes large means the log is also very large, right? At the same time, the similar function log of b to the base a tends to minus infinity if 0 less than a less than 1 and b tends to infinity. Okay, if this is the case, it becomes close to minus infinity. So the most common logarithm is base 10 that we need to remember. Okay, then let's move on to the next point under this. Say if x is less than 0 and a is greater than 0, right, and a is not equal to 1, right? If you see, this is the case, a is greater than 0 but x is less than 0, right? It means x is a negative term, right? This implies log of x to the base a, right, is going to be a complex number or imaginary. This is imaginary. That does not exist. Only imaginary. Okay. Then the next one is, so if a is greater than 1, this implies the log of x to the base a takes several possible values, right? This is going to be a positive quantity if x is greater than 1. This is going to be 0 if x is equal to 1. This is going to be a negative quantity if 0 less than x less than 1 is the condition. So this log of x to the base a has 3 possibilities. That is when a greater than 1. Let's go for the other case. If 0 less than a less than 1, right, then this implies the log of x to the base a will be positive, right, provided 0 less than x less than 1. So it is between 0 and 1. Okay, and it is 0 if x equal to 1. It is going to be negative if x is greater than 1. So have to remember several points related to the log function. Okay, next we move on to the next important property. This is something like, if I write simply a log of 1 to the base a, log of 1 to any base is 0, right, provided a greater than 0 and a not equal to 1. Then next one, log of a to the base a is always equal to 1. Again, the same condition, a should be greater than 0 and a is not equal to 1. Right. And the next one. So all these properties are important. Okay. If I have the log of a to the base 1 by a, right, this will be minus 1. Same condition, a greater than 0, a not equal to 1. All right, now let us try to solve some of the very basic fundamental problems related to log. Right, we might have to use these properties as well. So first one is very simple, right? Find the values of the following. First one is log of 27 to the base 9. Okay, let me call this is equal to x, because anyway I want to compare it and with the standard equation so that I can find out, right? So this means log of so we understood that if at all I have a to the power x equal to b, then I am going to call this as, right, the x equal to the log of b to the base a. This is my very fundamental equation. Right, now compare this. So x is as it is, a and b are 9 and 27, right? So this implies my actually what I'm supposed to find is, look at a is 9. 9 to the power x is equal to 27. This is the equation which you need to solve. Okay, but I cannot directly raise it to the power 9 cannot be directly, 27 cannot be directly written in terms of 9. For what I'll do, I'll write 3 square to the power x is equal to, I know that this is 3 to the power 3, right? 3 into 3 into 3. So I can actually rewrite this as 3 to the power 2x is equal to 3 to the power 3. So what you can do, you can say that 2x is equal to 3. This implies x is equal to how much? X is equal to 3 by 2, right? Yes. So the log, this means the log of 27 to the base 9 is equal to 3 by 2 or 1.5. Is the right answer. Okay, so I just have to remember this equation and I need to solve, right, for x ultimately. Okay, that was the question number 1. Now let's move to the next question. Question number 2 is log. Okay. Log of say 324 to the base 3 root 2 equal to how much? Right, as per the rule, I'm going to call this right hand side equal to some x. My intention is to solve for x. Okay, right. So how can I convert this? This means I have to write a to the x. A to the x is 3 root 2 raised to the power x should be equal to 324. Okay, so this gives you one idea that I have to factorize in terms of 3 and root 2. If root 2 not possible, you can do it in terms of 2 itself. Let's try that. So 324, I divide this by say 2, right? I think 162. So 2 is a factor. Again, try to do it with the 2, right? This is 8 and 1. So 2 is a factor. 2 is repeated twice, and let me write 3. So 327, then 3 as 9, then 3 into 3, then 3 into 1. Okay, now this is actually pretty straightforward now. Therefore, 3 root 2 to the power x is equal to, I can write 3 repeated 4 times. So 3 to the power 4 into 2 to the power 2. Right? I can see 3 to the power x, but I need a root 2 here. How do you bring a root 2? right? I have to raise the common power for 3 as well as root 2. That is possible, right? Now, if at all I write in this way, so this is 2, but what is 2? 2 is equal to root 2 square, right? So I can write a 2 as root 2 square. So this is nothing but 3 to the power 4 into root 2 to the power 4. Now you see you can take common. The power 4 is common. So this is 3 root 2 to the power 4 is equal to 3 root 2 to the power x. So this implies x is equal to 4. So use a calculator, write 3 root 2 raised to the power 4. Right? You will definitely get 324. 4 is the answer. All right. Okay. Next question. Log 27 root 3 to the base 1 by 9 equals to how much? So I'll call this is equal to say x. Right. And now according to the fundamental equation of log, this is 1 by 9 raised to the power x should be equal to 27 root 3. Okay. Now the common thing that we can observe in 9, 27 and root 3 is 3. Let's try to write everything in terms of 3. Right. So can we write 1 by 9? 1 by 9 is 1 by 3 whole square, right? So 3 melgade bandre, this is 3 to the power minus 2i, right? Which is 1 by 9. 1 by 9 equals to what? 1 by 3 square. So that is equal to 3 to the power minus 2. So 3 to the minus 2 to the power x is equal to 27. 27 is 3 into 3 into 3. So 3 cube into root 3 means 3 to the power half. So yeah, we are able to write everything in terms of 3. So this is 3 to the power 3 plus half. 3 plus half is 2 to 3, 6, 7 by 2. Right? Okay, now I think we get an answer. So this means 3 to the power minus 2x is equal to 3 to the power 7 by 2 implies minus 2x is equal to 7 by 2. So x is equal to minus of 7 by 4. X equal to minus 7 by 4 is an answer. Yes, we have this. Okay, next question. Right, find log of 0.008 to the base 0.2 equals to how much? So in this case, this value is equal to, if we call this is equal to x, x is equal to 3, because 0.2 raised to the power 3 is equal to 0.008. Okay. All right. Next question. Two to the power 2 log of 5 to the base 4 equals to how much? What we can do here is we'll try to simplify this in the following fashion. This is equal to, I can try to write this as 2 to the power 2 to the power log of 5 to the base 4. Okay, this is nothing. What is the 2 square? 2 square is 4. 4 times log of 5 to the base 4. So this is like you have to find out the value a to the power log of b to the base a. There is a property, right? This is equal to b. Right, we use this property. So this is equal to a is 4 here, 4 to the power log 4 log to the base 4 of 5 is nothing but therefore 5. Okay, right. Then next question. Log of 5 plus 2 root 6 to the base 5 plus 2 root 6 equals to how much? In this case, this is equal to 1, right? Very simple answer, because 5 plus 2 root 2 6 is equal to 5 plus 2 root 6 to the power 1 itself, right? Okay, next question. Log of 5 minus 2 root 6 to the base 5 plus 2 root 6 equal to how much? All right, so this is equal to minus 1, because 5 plus root 6 is equal to 1 divided by 5 minus 2 root 6, right? We use that property to get this answer. Right. Okay, then we have one homework question to solve. The question is 0.4 raised to the power minus 2 times minus minus log of 1 by 3 plus 1 by 3 square plus 1 by 3 cube. Okay, all the terms till infinity to the base. The base is 2.5. Okay, looks very complicated but very simple.